This video is a brief overview video before we jump into the details of pi bonds, which are basically what lead to the creation of double bonds and triple bonds. So let's just do a quick recap of hybridization as we've seen it so far. If we see a molecule, for example, like NH3, like this, you can easily figure out its hybridization by counting the electron regions around it. So around nitrogen, we can just come up with hybridization by doing this is one electron region, this is another, this is another, this is another. And essentially the way you would attribute that to hybridization is you could say, well, this first region is an S. Then as soon as you have an S counted, you go into the P's. So this is a P over here, this is another P over here, and this is a P over here as well. And so what we have is sp3. If we had anything above that, then you would go into the D's up until D2. So the hybridization of nitrogen in NH3 is sp3 hybridized. And if we had something, let's just say like this, so let's do SF6. I'm not going to do all the lone pairs because I'm just going to focus on the hybridization of sulfur as opposed to the fluorines that surround it. For SF6, we have SP1, P2, P3, D1, D2. So we have SP3, D2. And that's a shorthand way to find the hybridization. The other thing we saw as well is that these single bonds that you see here, these single bonds, we refer to them as sigma bonds. So each single bond is made up of a sigma bond. Sigma with the Greek representation here, sigma bond. And that was really a direct overlap of orbitals. So in the SF6, we have an overlap between a unpaired P electron in the fluorine and an unpaired electron in the sulfur, based on its hybridization, an sp3 D2 hybridized one. I'm not going to do the exact shape, but I'm just going to show you that the overlap would have been a direct overlap. So this is a sigma bond, and that leads to the creation of these single bonds here. So in SF6, you have basically 6 sigma bonds that are present, 6 sigma bonds, sigma. And then in nitrogen, in ammonia, we have 3 lines here. So that means that we have 3 sigma bonds, 3 sigma bonds. So 3 sigma bonds over here, and then 6 sigma bonds over here. Now let's go take a look at situations where you have multiple bonds, like double bonds and triple bonds. So here we have carbon dioxide, and I'm going to do the hybridization of carbon. And it's the same process that we would do if we want to calculate hybridization with something with single bonds. You just count the electron regions, and the multiple bonds count as one region each. So this is an sp hybridized. So the carbon here is sp hybridized. If we had something like this, let's do, and we want to do the hybridization of the carbon here, and again, it's sp hybridized. So sp hybridized for the carbon. And you can go look at the other atoms as well, but we're focusing on a central atom. So hybridization is done the same way, whether you have single bonds, double bonds, or triple bonds. But where things will differ a bit is with the type of bond overlap that you have. We had said that when you have single bonds, that's formed because of a sigma bond specifically. Now, we're going to see the process of multiple bonds formation, double bonds and triple bonds. And so each multiple bond consists of one sigma bond. So basically, when you look at, let's say, carbon dioxide, and let's focus just on one of the double bonds, it doesn't really matter which one, this one here. One of the bonds in here is going to be a sigma, and that's formed from the direct overlap, as we saw above over here. But another bond in the double bond is going to be formed by a different type of overlap called a parallel or indirect overlap. We'll see later on, but we call it a pi bond. A pi bond. The sigma bond is a stronger bond, the stronger of the two bonds contributing to this, and the pi bond is a weaker one. So we have a sigma bond and a pi bond within a double bond. Here we have a sigma bond, and here we have a pi bond within the double bond. Now, in the triple bond, let's go over here. a triple bond is made up of a sigma bond and then 2 pi bonds. 2 pi bonds. So when you have a double bond, that's going to be made up of 1 sigma plus 1 pi. A triple bond is going to be made up of 1 sigma plus 2 pi bonds. The sigma portion is the strongest part of the bond, and then the pi portion is the weaker part. A single bond is made up of 1 sigma bond only, 1 direct overlap. The strongest of these bonds is the triple bond, and the weakest is the single. And the reason is because, yes, sigma is the strongest bond, but if you think about it, the multiple bond has sigma plus a weak bond. The triple bond has sigma plus 2 weak bonds, so it's going to be a little bit stronger. When these bonds react, when a double bond or triple bond goes through a reaction within a molecule, the parts that break are generally the the pi parts that break, and the sigma requires more energy to really break that apart. So if you're doing just a reaction where you're adding stuff to a molecule and you're not tearing the molecule apart, so to speak, you're usually going to be breaking the pi bonds first. So right now, what you should be able to do is, if I give you a molecule, so suppose I gave you this molecule here, you should be able to go through it and find the hybridization of basically any atom within it. And you should also be able to tell me how many sigma and pi bonds there are. So let's just start with that. You can try it on your own first, pause the video and try it out yourself. Let's start out with just trying to figure out how many sigma bonds there are. So in this molecule, I have a sigma bond in the single bond, a sigma bond in this single bond here, a sigma bond here, and a sigma bond here. Don't forget now, in your double bond, you also still have a sigma bond present. One of the bonds there is sigma. So we have 1, 2, 3, 4, 5 sigma bonds. And then don't forget that we have a double bond, so that means that we have a pi bond there as well, and 1 pi bond. And then you can go through and do the hybridization of the atoms. So we can look at, let's just call this carbon number 1 here. This is sp2 hybridized. So this is an sp2 hybridized carbon. Let's carve this carbon number 2. This is an sp2 hybridized. So this is also sp2 hybridized. And then you can look at your hydrogens. Well, they're just S, 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 S. It doesn't really take hybridization because it just has that one orbital anyways. So it's S overlapping with the hybridized sp2 of the carbon. And these are all direct overlaps here. So if you can do that, you understand the process of identifying sigma and pi bonds. You understand how to do a shorthand method of finding the hybridization of atoms in molecules. For the most part, you know how to demonstrate hybridization in molecules using energy level diagrams when it comes to single bonds to form that are formed of sigma bonds specifically. And then in this particular lesson that we're going to dive into, we're going to see how to show the hybridization and the overlap process for multiple bonds forming. So we're going to show the pi bond formation with the indirect overlap. But first, make sure you can do questions like this. We'll do one more together just to make sure you have a good understanding. So let's just go through, let's do this one here. So we have a molecule like this, and we'll go and calculate the number of sigma bonds. So in the single bond, there's a sigma, and there's a sigma here. Don't forget the triple bond is made up of 1 sigma. So that's 3 sigma bonds. And then the triple bond is made up of 2 pi's, a pi and then a pi. So 2 pi's. And you can go do the hybridization of each atom. So the carbon, for example, here is sp. So sp hybridized carbon. And then over here, let's call this carbon number 2, sp, 2 domains, right? So this is going to be sp as well. And then, well, the hydrogens are simply S and S. Those are some basic skills you should review before you go into the full lessons on pi bonds, hybridization, of multiple bonds.